Hello and welcome. In today's lecture, we will look at block diagrams for some very simple process systems. The idea being the process structure, how it determines the block diagram structure. So let's first look at a non-isothermal Cstr. So what we have is the reaction A goes to be occurring in the liquid phase Cstr, and there is a jacket, and we are assuming that the jacket has a constant temperature Tj. And this is a good assumption because in practice what is done is you know you have coolant circulating by coolant is circulated in the jacket by a high throughput pump, and this is the coolant, and because the circulation rate is very high, therefore the temperature rise as the coolant moves from here to here is negligible, and therefore in effect what the reactor sees is a jacket at a constant temperature Tj. Okay, so this is a reasonable assumption. And what we are interested in is the block diagram structure, cause and effect structure, for how T naught affects T, the reactor temperature, and concentration of the reactant A leaving the reactor. That's what we are interested in. We want the block diagram for the effect of T naught on T and Ca. So if you think about it, if T naught changes, obviously there will be a immediate direct effect on T. Okay, but as the reactor temperature changes, reaction rate will change, because reaction rate has that Arrhenius dependence. As reaction rate changes, the rate of consumption of A will change. If rate of consumption of A changes, Ca will change, and if Ca changes, reaction rate will further change. And if it's an exothermic reaction, uh, that will cause another change in T. You see, so there is this cascading effect. So if T changes, so let's call this the transfer function effect on T of T naught, direct effect on T of T naught. But then as T changes, so this is T, as T changes, it will cause a change in Ca. Let's call this Ca. So this would be G effect on Ca of T, transfer function relating Ca and T. Now if Ca changes, T further changes. So you'll have a transfer function that causes T to change due to a change in Ca. So this GTCA is effect on T of change in Ca, and because this is affecting T, this is going to add up here. See, so you got this feedback loop in there. So this is the block diagram. The essential feature is the coupling between the material balance and the energy balance. This coupling is because of this feedback loop. This coupling causes this feedback loop. T naught affects the energy balance affects the temperature affects the reaction rate affects the material balance affects the composition affects the reaction rate in turn affects the temperature again. So there is this two-way interaction which is the cause of this feedback loop in this system. So here's the block diagram drawn for you, and as an exercise you can draw block diagrams for the effect of Ca naught, F naught if Ca naught changes, if F naught changes, or if Tj changes. For each of these, what is the corresponding block diagram for the effect of a change in any of these variables on T and Ca? You should do that as an exercise. Let's look at another interesting example. An exothermic reactor coupled with a feed effluent heat exchanger. This is something that is often encountered in practice. So what you have is cold feed, this is cold, going into a reactor, and the reactor is hot. Because the reactor is hot, highly exothermic reaction, the reactor exit stream is hot. So what you do is you preheat the cold feed to the reactor temperature using a process to process heat exchanger as shown here. So these reactor feed effluent heat exchanger systems are quite common. It improves the energy efficiency of the process. What we would like is a relationship, a block diagram relating change in T naught. If the temperature here changes, how does T2 change? That's what we want. Block diagram for effect of T naught on T2. Okay, so here again we start applying our mind, whatever little bit we have. If T naught changes, T1 changes. If T naught increases, T1 will increase. If the inlet to the reactor is hotter, it's an exothermic reaction. Reaction rate will be faster. Reaction rate is faster, therefore more heat will get released. If more heat gets released, T2 will rise. If T2 rises, then the hot side of the feed effluent heat exchanger will be hotter, and therefore more heat will get transferred across the tubes of the feed effluent heat exchanger, and therefore T1 will rise further. So again there is this feedback loop due to the energy recycle that's occurring in the feed effluent heat exchanger. So if I want to draw a block diagram, the block diagram is going to be pretty simple. G effect on T1 of T naught. So input is T naught, output is T1. If T1 increases, effect on T2 of T1. As T2 increases, so this is T1, this is T2. As T2 increases, T1 will increase again. So there is a transfer function that will cause an increase in T1. There is a transfer function that relates T1, that relates T1 and T2. So this transfer function is change in T1 due to a change in T2, and this change in linearized systems will add up. Well, and that's it. So now if you look at this guy, the overall transfer function from T naught to T2, so G effect on T2 of T naught is going to be equal to whatever is in the forward path. Forward path is G T1 T naught times G T2 T1 divided by 1 minus whatever is in the feedback path. So feedback path is G T2 T1 times G T1. Yep. Okay. Now typically reactors will be very large and heat exchangers, comparatively the dynamics of the heat exchanger will be much faster compared to the reactor. So as a approximation of the dynamics, let us say the dynamics of the heat exchanger are instantaneous while the dynamics of the reactor are maybe a first order lag. So what we are saying is uh, this corresponds to the reactor, so this is a first order lag. So what we are saying is this will just be a gain, a pure gain. So K, we'll just say 1 0 K 1 0. This is also associated with the heat exchanger, so this will also be much faster. So we'll just say that this is also a pure gain. So K on 1 of 2, and this guy we will say is a first order lag. So K on 2 of 1 divided by some time constant of the reactor plus 1. Now if we substitute this into these transfer functions into this, what we will get is G T2 T naught is going to be K 1 0 multiplied by K 2 1 divided by tau s plus 1, this whole thing divided by 1 minus K K 2 1 into K 1 2 divided by tau s plus 1, and this guy is going to be, if you just solve it and put it in standard form, it's going to be K1 naught K21 divided by 1 minus K21 K12 divided by tau s plus 1 tau divided by 1 minus K21 K12 times s plus 1. So you can see the gain of the system with that feed effluent heat exchanger in there. This is the new gain, we'll call this K prime. This is the new constant, time constant, this is tau prime, and you can see that K prime is much greater than K, and you can also see that tau prime is much greater than tau, because this, and you can also see that if K2 if this product K12 K21, if this is greater than 1, then this guy becomes negative, and therefore you get an unstable system. So thus the recycle of energy through the feed effluent heat exchanger A causes the gain of the system to be significantly larger, significantly slows down the dynamics because the time constant is again significantly larger, and if the product of the gains K21 K12 is greater than 1, it also results in instability. This is another example of recycle or feedback, positive feedback in this case, because the overall sense of the feedback in this loop is positive. Positive feedback having the potential to cause instability. So this is the block diagram. The transfer function, and if I assume instantaneous dynamics of the heat exchanger and first order dynamics of the reactor, then the transfer function simplifies to this guy, much larger gain, much larger time constant. So in summary, recycle can cause, or usually recycle can result in a much higher gain for the process system, much larger time constant, that is slower dynamics, significant slowdown in the dynamics, and also possible instability, condition being K12 times K21 being greater than 1. Now obviously you cannot have these kind of reactors suffering from instability, so in practice what is done is, you have the reactor, you have the heat exchanger, but you'll have a heater in the middle, and even though the temperatures are such that all the heat that is required in order to raise the temperature from T0 to T1 can come from the hot effluent stream, hot reactor effluent stream, you will still design the FEHE such that only, let us say, 70% of the heat comes from the FEHE, remaining 30% comes from the heater. And now what happens is, what is the heating duty? That's a controlled degree of freedom that you have introduced in the design of the process, and if you control the temperature, you see, because this temperature is now held constant, the buildup of temperature due to energy recycle is prevented by removing as much heat or adding lesser heat in the preheater, so that the temperature remains where it is supposed to remain. So this is what breaks the feedback loop. This temperature controller breaks the feedback loop. The temperature controller thus breaks the feedback, energy feedback. And in this way, real systems will always be stable, because you choose not to extract the maximum amount of energy that you can extract from T2. You choose to extract much lesser and install a preheater to give a trim preheater. This is called a trim heater, and with that trim you stabilize the temperatures and prevent them from running away. Okay, this is how it is done in practice. But without the heater, you see the potential for runaway, because if this goes up, this goes up. If this goes up, exothermic system, this goes up. If this goes up, hot side of the feed effluent heat exchanger becomes hotter, so more heat gets transferred across the heat exchanger, and therefore this goes up further. If this goes up further, this you see, this is the positive feedback. Positive feedback. Yeah. So the key thing is, the process structure here dictates that there has to be a feedback loop in your block diagram structure. Now let's look at a distillation column, and what we want to do is we want a block diagram that relates the effect of L on the overhead vapor composition. It's not a it's actually a distillation column section. Not the entire column with the condenser and the reboiler, but just okay. Alright, so a tray section. Now let's start thinking about it. If L increases or if L changes, vapor, there will be a direct effect on the vapor. Vapor composition changes a certain way. And let us just say this is G, the transfer function relating the change in vapor composition due to a change in the liquid flowing into that tray. So there's a tray, there's what's leaving the tray, there's what's entering the tray, and we are saying the transfer function relating this to that is this guy, GVL. Relating L to Y, the transfer function relating L to Y is GVL. Effect of the liquid rate into a tray on the vapor mole fraction. Okay. But then the vapor mole fraction also gets affected by the vapor that's coming from below. So there will be the effect on the vapor leaving a tray due to the vapor coming from below. And this would be Y1. And these are all summations. Now the vapor coming from below, you see, there is a secondary effect. That secondary effect is as follows. If liquid changes, vapor mole fraction changes, and so does the liquid mole fraction on the tray, and therefore this changes, and because this changes, this causes an additional change in this, which causes an additional change in this. You see? So if there is a change in the vapor, there is a corresponding change effect on the liquid due to a change in the vapor, on the liquid leaving the tray due to the change in the vapor, not into the tray but leaving the tray. So this is different from that. So there is this vapor that's coming from below. This liquid that has now changed will cause a change in the vapor leaving the previous tray, that is this guy, because now the liquid composition has changed, therefore there will be a change here, and this is the effect on the vapor leaving a tray due to the liquid into the tray. and you can carry on like this. So if you, so this is y1, this is y2, vapor leaving the second tray. Change in vapor leaving the second tray will cause a secondary effect on the vapor leaving the previous tray through a transfer function GLV. You know, this cascade will go on and on and on up to n. This would be y3. Is that right? Yeah, y2. Yeah, that's all right. And keep going. There will be a block diagram here. I'm sorry, I forgot. Uh, so the effect of the vapor leaving the second tray, it affects the liquid going into the third tray. The change in the liquid going into the third tray affects the vapor leaving the third tray, and that gives the composition of the vapor leaving the third tray. And you will have, and keep on going like this down. I have drawn this cascade laboriously, and let me just show you that cascade. Here's the cascade. So let's think this through again. Let's look at this guy. This is the effect on the vapor of L reflux. The vapor changes. In response to that change in the vapor, the liquid leaving the tray, that is this guy, changes. So the liquid goes on to the next tray, and because the liquid onto the next tray is changing, so if this is L1, this is liquid onto the next tray. L1. This is liquid going on to the next tray. If this is liquid going on to the next tray, it affects the vapor through GVL, like here. That gives you Y2. But then there's a secondary effect. The change in vapor leaving the second tray, which is this guy, causes a change in the liquid going down. That is because of this guy. So you start getting L3 here. And this change in liquid causes a change in the vapor leaving the third tray, which is this guy. So from here you come here. This guy then causes, Y3 then causes a change in the vapor, change in the liquid leaving the third tray, that is this guy, which in turn causes a change in the vapor leaving the fourth tray, which is this guy, and so on and so forth. See, so you get this cascade of transfer functions that are connected in this way, and this cascade captures the essential feature of secondary effects. There is the direct effect, but then there is this secondary effect. There's the direct effect, but then there are these secondary effects, and these secondary effects will significantly slow down your dynamic response. Maybe we will do a lab exercise that does something like this, that does things on a process transfer function that is a cascade as shown in this example, in this screen, in this slide, on this slide. So I haven't tried it, but this might be an interesting cascade, and you can go on till n, and n can go till infinity, n trace or infinite trace, and what I would like you to attempt, I have not tried it, but maybe it's worth trying. Derive the transfer function relating this to this for this cascade with maybe n trace. So these are actually interacting lags. So there are lags in series, but then there is this interaction. So these are actually interacting lags in series. So what would be the transfer function for n interacting lags in series? Maybe you should try and solve this block diagram and get a neat expression and see if there's a pattern that emerges. So in summary, we have looked at some very simple systems, and based on the process structure and the flow of causes and effects, proposed very simple dynamic block diagram models to represent the dynamics of these simple systems. And the key takeaway is that the physical process structure determines the block diagram structure. And the other key takeaway I would say, which I have not listed here, is you got to think through how the the chain of cause and effects is flowing. In the CSTR example, we got a feedback loop because of the coupling between material and energy balance. In the reactor FEHE example, we saw that the energy recycle causes a large increase in process gain and time constant. It is also possible that if the recycle is very large, the process may become unstable. Distillation column example is a bunch of interacting lags in series. I'm sure there are conditions for stability there also, because you got feedback loops there. Maybe you can derive them as an exercise. With this, we come to the end of this brief lecture. Thank you for your kind attention. Hope to see you next time. Thank you and goodbye.